Yeah, and you can also tell from this little dot here, if the dot is on, we're recording. Okay, sorry about that. To recap, University of Canterbury's website is a whole hell of a lot slower than the University of Victoria's website, even though they're both in New Zealand. And University of Victoria's website is about the same speed as our own website, or even maybe a little faster. So how did that work? We pinged the University of Canterbury website here, took a quarter second, and we pinged the University of Victoria, took about 5 milliseconds, 5,000ths of a second. Please get the units or the prefixes. Milli as a thousandth, micro is a millionth, nano is a billionth, right? Okay, and the University of Illinois at Chicago, same, about 10 milliseconds, 5 to 10 milliseconds. All right, so yes, let's see. How far is it to New Zealand? It's probably about a quarter way around the world. That's 10,000 kilometers, maybe. So it's 20,000 kilometers round trip. Let's see, how long should it take? 20,000. Yeah, 20,000 kilometers, and light can go 300,000 kilometers per second. So it should take 66 milliseconds round trip. If it's 10, it's probably a little further than that to New Zealand. But anyway, the shortest it could possibly take is 66 milliseconds to go round trip to New Zealand, but we got an answer in 10. And so something's going on. We can tell if we maybe can try this. Just like that, see what happens. Ah, lame. All right, let's try this one. Really? These losers don't put in their PTR records. All right, let's do this instead. They don't have a choice. Who is, you don't get to have an IP address unless you're in the whois register, so that's probably okay. Oh, this doesn't look like the University of Victoria a whole lot. It's called Fastly, and they seem to live in San Francisco. Let's try the other one. Oh, that was probably the same one again. Sorry. Whereas this one looks a whole lot more New Zealandish, right? It's not Christchurch, by the way, it's one word. But that's in Canterbury, in New Zealand proper. Okay, so at least the organization is in Christchurch, where it should be. So the University of Victoria, they are making use of what's called a content distribution network. Fastly is one of many such providers. Let's see what we got here. CDN, Content Distribution Network, CDN. Fastly is one. You probably have heard of Akamai. You've probably seen Cloudflare, maybe. There's something else called Cloud Edge. AWS, I think. Lots of this sort of thing. Let's see, I think I had one. Oh, Edgecast I've seen. Right. All these, they are there basically to help you get your content to the customer faster. So it's not that we're paying any of these to help us. University of Victoria is paying Fastly to basically host their website all over the place. And so when you make a request, you get to talk to one of their websites, web servers, And which one kind of depends, but it should be one that's pretty close. That's the general idea. Let's take just a look at a bigger website to see how advanced it can get. I don't know how to unsplit this view. Let's see. There it is. Okay, great. So I'm just going to go to the New York Times website and get a dump of everything that's going on there. Let's stick this in a file. Oh. All right. Oh, great. Right. Let's do that a couple times. And we're done. Okay. So it looks like that. And just to, I want to kind of show off a little bit of tools that I think we will be using somewhere along the way. And if not, you'll be using it some other time. Awk is really fantastic. Who knows Awk? Nobody knows Awk. Okay, if you ever in your future life deal with a text file, like a log file or any other kind of structured text file, Awk is definitely what you want to use. So this file, I just want to see which host is it that what hosts are we talking to here? All right. So there's a whole bunch of lines like this, and I'm interested in the ones that have, like the ones that are sending to me, will be like these. So it says HTTPS and then a little arrow. Let's go like that. All right, so now I get, well, I guess all of the traffic looked like that. So this is a regular expression. I'm saying anything that matches this expression, let's just print that. But let's be a little more specific. I want the 1, 2, third word on this line is separated by default by space. So I want the third line, the third word. Oh, okay. And then I just want to see how much are we talking to each one of these. So we'll sort that, and then we'll count how many there are of each. And there it is. Okay, so we were talking to the New York Times, right? It's possible that there was some other things going on here because this thing keeps changing pictures, and you know, I have some other websites open and whatnot, but the majority of this traffic would be coming from this New York Times website. So here's quite a bit of Akamai. Akamai is the biggest CDN provider in the world. And then Amazon AWS, that's probably New York Times on its own, because if you look at these, there's just no New York Times. I tried to get to New York Times, but all the answers are coming from somewhere else. And that's probably because New York Times is using cloud services to run their own web servers. But that's only where they keep the sort of the dynamic content, things that change. I don't know, ads. For the rest, they're relying on various CDN networks to kind of deliver the contents. Let's see what are some other big ones. Okay, so who is this? That's Fastly. Okay. Let's get one other big one. Oh, I don't know what that is. It's kind of funny looking. Okay, but we had Fastly, we had, oh yeah, let's do that one first. Oh, there's Google. Okay, that's probably some advertisements. And well, there's going to be a few others represented too if we dig deeper, but let's not do that for now. Okay, so the general point is all these web services, basically anything big, they don't want to deliver the contents directly from their website. I think there's two reasons for it. For just a text website, you probably want it to show up quickly. Like, you want it to feel responsive. So what they do is they, every now and then, let's see, so here's our CDN, which has a lot of web servers all over the place. We'll just ignore that for now. They will just push every now and then new versions of their content to this CDN website. The browser, generally speaking, will go and ask the correct server, which will then refer you back. Check with the CDN, right? And then we go and ask the CDN provider to get the contents. So by pushing, yeah.
You said this is generally for like HTTP traffic. What about like streaming services?
Absolutely. Those are any sort of media services are going to do the same thing. So HTTP, like one reason to do this is that you want a responsive website. Another one is you are worried about your bandwidth. And so we'll get to that maybe in a little bit. But basically the CDN provider maintains a server here and a server here, right? And a server over here. And so the next browser comes, and now we contact the server. And how do we know which CDN server we should talk to? Right? The browser, the server doesn't really know anything about this. They will just say, oh, go and talk to Akamai. They have my content. Right? So now, how as a web browser do we know which Akamai server to talk to? They have some 120,000 servers. Any ideas? So it's going to be a URL, right? Back comes a URL with an image. It says something like that. You saw these, static, like this. You'll say like this, blah, image, some image name, right? That's what we want to fetch. So how do we get the right one? Well, I guess this one actually looks like we're cheating a little bit. This is reverse look up already, so that's a specific server, but it'll start by static akamai-technologies.com. And then some image URL. So how do we get to the right one? Akamai will have to tell us somehow, but how can they tell us? We haven't started yet. Like, I just want to talk to static.akamai, but it has to be the one in Chicago. It can't be the one in New Zealand.
Does it send like a list of IPs to try and based on like a quick ping back and forth, shorter, choose that one?
So how does it send the list?
Well, you talk to the server.
I talked to the New York Times server, yeah, but they don't want to know about Akamai stuff. They just say static dot. In fact, we can probably, we're a little short on time, let's not do it, but trust me, it'll say like static.akamai.com/New York Times image 5, right? But longer. They have to hack the DNS, all right? The only thing that they're giving us is something that says static.akamai.technologies.com. But if you change the DNS server, this may be a good reason to know how to do this and see, I don't know. If it was 20 years ago, could have been a billionaire, you know, but too late. So you look up static.akamai-technologies.com, and what comes back is a different answer depending on what your IP is. Like the DNS server gets an IP address, and this is only the first time you look up this thing. You get an IP address back and says, yeah, talk to this server, right? And after that, this address will always resolve to a local server, which has your stuff. How can they know? Okay, actually I should write that down. So we have a DNS resolution in a different CDN server based on requester IP. So we have this DNS server, and it's getting a request, and the request looks exactly like whatever we sent, right? So all it has about us is our IP address, maybe a source port address. So now, how does the DNS server know which IP address it should send back? What do you think? Yeah.
If they know your location and they know the location of nearby servers, they can just.
They don't know my location. They just have an IP address. Could be anywhere in the world.
Doesn't say a lot.
Okay, maybe. I mean, yes and no. I think two IP addresses that have the same prefix, a long way, but then just differ in the last few, they're likely to be in the same place or nearby each other. But other than that, like if something starts with 10 dot or it starts with 11 dot, one is in Australia and the other one is right here.
I know there's like geolocation services that can give you like a very rough estimate of where the IP is located.
And that's what these guys will have to implement. Well, in some sense, they have to figure out how to do that. The geolocation service does not exist on the internet. It's a product, much like this CDN. So, in the case of the CDN, we want to find the closest server in either latency or bandwidth. Right? We want a server that will go fast and that will, like, you can download things quickly. And we'll talk about the difference between latency and bandwidth later. But one is you get a response quickly for a small request, that's latency. And the other one is you ask for this big file and it's finished downloading quickly. So we want one of those two. Let's start with the latency. So we want to know for an IP address which server is the closest? And we're the DNS server now. So how do we see, like, are those two closer or are those two closer? If we there's nothing else here. Let's not rely on any further services. We just have our DNS server, your packet, and of course we have the machines on the other side, like our web servers. Any ideas? That's what they had to solve to build Akamai. Yeah.
Do they just ping your IP from all of their different systems?
Well, okay. So it's a start. Okay. So the DNS request comes in, and we see the IP address, and now we ask all of our web servers, 120,000 of them, to ping that IP address and see what response, which response comes quickest, assuming that the connection doesn't die. Or, modem burns or something, and then just say, okay, you're going to talk to the one with the lowest number. That'll work. It's not going to be any faster than just talking directly to the. It'd be better to not use the CDN, of course, but at least now we've resolved it, and after we've done that one resolution, now it's going to work pretty okay. But then there's millions of users and 120,000 of these servers. We're going to kind of run out of internet bandwidth. It'd be better not to do it that way. Any other plans? So it so happens IP addresses don't really move around a whole lot. Yeah.
So I wonder, can we hash the IP to try to get it to turn it into an IP that equals a CDN server? I don't know.
The problem is the IP addresses don't have a lot of location information in them. In principle, every IP address could be in a different place in the world. In practice, they're usually grouped in bunches of 256 or more. But yeah, there's many groups. Yeah?
But what it's starting to say, the IPs don't change very often, but if you're working like off a Comcast network or something at your home, your IP changes.
Yeah, but it's always going to be a Comcast IP. It's always going to be even like a Chicago Comcast IP. But you may get a different one. Your neighbor maybe has the one that you used to use. Right? So in that sense, yeah, you'll find that they all start with pretty much the same prefix, and they change a little bit at the end. At UIC, we have the, 131 is our sort of prefix. 131, 193, something, and that's us. Okay, but knowing that these IP addresses don't change a whole lot, it'd be better to not try to figure out the closest server on the fly. Like when someone makes the request, it's already too late. We should respond immediately. But we could do it ahead of time and just keep a lookup table, right? So in principle now, how many addresses are there?
For 4 or 6.
What's that?
For
Oh, IPv4. A lot of addresses, correct?
255, 256 to the 4th.
256 to the 4th, that's one way to put it. 4 to the 32nd is another. Yeah, it's 4 billion about. 4 billion addresses. So in principle, you know, that's many. And we don't actually need that granularity, but in principle, you could just keep an entry for each one of them. And over the course of a few days, ping every damn one of them, right, from every server you have, and then you're done, right? Now, you can be a little more efficient. We'll find out more about autonomous systems and such later, but as you remember, perhaps, when you say who, if we say who is about any address, it says something like this. So that entire group of addresses belongs to the same network. So we could maybe, at least for starting, we could say, okay, if I ping one of these, probably the answer will be the same for all the other ones of the same network. So now for every new customer IP that comes in, you just see, oh, do I have a record? Do I have one of these subnets already? If not, I'm going to have to resolve it. For now, just go with some default. Next time they come back, I have the correct answer for this customer. So now they'll always have a good server to talk to. So yeah, in general, that's the idea for latency. We can just ping everyone. We could do it sort of reactive by just doing it for the people who actually come and use Akamai, or we could do it for every subnet out there if we have some way of discovering good IP addresses. Maybe you could enumerate them. They're not that many. So, okay, what about bandwidth? Latency, pretty easy. Ping them all, right? We can't ping them from the DNS server. The DNS server is not involved here. It just gets the question. It has to be the web servers that check, like they try to ping the destination address. And if we get a response by ping, then it's good. If we're not getting a response, then we can at least use traceroute, which gives you ping times along the way, and maybe you get the last hop or something. So we can sort of passively get this measurement. What about bandwidth? So it could be that the network looks something like this. We haven't talked too much about internet topology yet, but I have my server and client, and then have another server over here. But it happens to be that this one here is a fat pipe, and this one's relatively small. So ping times here, because it's short, is really good. We'll respond quickly because it doesn't take a long time to transfer a small message. So it doesn't matter how thick the pipe is, it matters how long it is. In this case, ping times will be longer, but because it's a fat pipe, once you start sending a big image or something, it'll finish up faster because you can get more kind of volume per second. Megabits per second, really. Right. So how do we resolve this one? Here the problem is you can't, like the client isn't there like to respond saying, oh, let's do a bandwidth test. Right? Client doesn't do that. That was your idea?
Yeah.
Yeah. Okay.
Maybe store in the server how much bandwidth they have, where they can produce.
The bandwidth, okay, so the problem here is not that the server doesn't have much bandwidth. It could just as easily look like this. Right? We have a fat pipe to this client over here, a thin pipe to this one. It all depends on basically what kind of cables you have going between the various machines. Yeah.
Maybe some sort of ratio between number of users already connected to that server and.
Oh, I see. Right. Yeah, so that's definitely makes sense. That probably Akamai wants to keep track of like how much load is there on each server and try to spread the load among several different ones if a server gets overloaded. Yeah, it's not really a network bandwidth constraint in that regard, but that's an important one too. It's called load balancing, and they do a lot of that. Usually, if you get too much load, in this case, you would just put more servers next to each other in the same location. Well, another idea that you could try is you just give it one server. Like you have some candidates. These around are in the same area. They have low ping times because we know that. I don't know which one is best. So let's just give them this one. See how it goes. And next time someone comes in from the same IP range, you give it a different one. Right? So now you're sampling different server choices. And turns out one of them goes faster than the other. You can tell from the server how long it takes to finish everything up. It's not like with FedEx or something. You give them a package and you don't know how long it's going to take. It's more like sending water down a pipe. So you know the water is finished. Okay, so basically we have to sample. That's the general idea. We have a few different choices, and now we have to start sampling to see which one should we be working with. But again, the hope is that these things don't change too quickly. So over time, we can kind of converge on one machine that will run quickly for us. Of course, I should mention something about where these things are located too. So Akamai will have, and I think Fastly as well, will have machines distributed all over the place at internet service providers throughout the country. Right? So Comcast will have like an Akamai server in the western suburbs and in the eastern suburbs and in the northern suburbs of Chicago and all over the place. It's not the same for Netflix. Netflix is a little different because they have such enormous amounts of data. Right? They're hosting, I don't know how many movies, but there's a lot of movies and large bandwidth constraints. So they're a little more centralized. They keep all their movies in various data centers, all hosted by Amazon Web Services. So they will have an East Coast and a West Coast and a European and so on data center where they keep all their movies, keep copies of the movies, and you get kind of shuffled to the right large data center, but you don't get this fine granularity that you get with Akamai. And the reason is with Akamai you really care about latency. You want a quick response time, whereas with Netflix you just want to conserve bandwidth. You don't want to be using, if you're sitting in New Zealand watching movies, you don't want to be using the Pacific cable all the time to get movies from San Francisco. No, you keep a local copy of all your movies in New Zealand. Okay, we ran out of time. I have to talk a little bit more about the sort of various applications of content distribution networks next time. By the way, next time will be recorded only. I'm in DC reviewing some proposals for the National Science Foundation. So I'll be back on Wednesday. All right, I'll post a lecture online.